Good morning. This is part 2 of module 3. Electromyography or EMG. Electromyograph is an instrument used for recording the electrical activity of the muscles to determine whether the muscle is contracting or not. And this instrument is useful for making a study of several aspects of neuromuscular functions, neuromuscular conditions, reflex responses, etc. EMG measurements are also important for the myoelectric control of prosthetic devices or artificial limbs. This use involves picking up EMG signals from the muscles at the terminated nerve endings of the remaining limb and using the signals to activate a mechanical arm. This is the most demanding requirement from the EMG, since on it depends the working of the prosthetic device. The amplitude of the EMG signals depends upon various factors, for example, the type and placement of electrodes used and the degree of muscular exertions. A typical EMG signal ranges from 0.1 to 0.5 millivolts. They may contain frequency components extending up to 10 kHz. Such high frequency signals cannot be recorded on the conventional pen recorders, and therefore they are usually displayed on the CRT screen. EMG is usually recorded by using surface electrodes or more often by using needle electrodes, which are inserted directly into the muscle. The surface electrodes may be disposable, adhesive types, or the ones which can be used repeatedly. A ground electrode is necessary for providing a common reference for measurement. Needle electrodes pick up spike type voltages, while surface electrode picks up many overlapping spikes and therefore produces an average voltage effect. Instrumentation system for EEG. The electrodes pick up the potentials produced by the contracting muscle fibers, which can then be amplified and displayed on the screen of a cathode ray tube. It is also applied to an audio amplifier connected to a loudspeaker. A trained EMG interpreter can diagnose various muscular disorders by listening to the sounds produced when the muscle potentials are fed to the loudspeaker. This block diagram shows a typical setup for EMG recordings. The oscilloscope displays EMG waveforms. The tape recorder is included in the system to facilitate playback and study of the EMG sound waveforms at a later convenient time. Modern EMG machines are PC based, available both in console as well as laptop models as shown in figure. The preamplifiers used for EMG are generally of differential type with a good bandwidth. The input impedance of the amplifier must be high. The preamplifier provides an output with low impedance and should have very high common mode rejection ratio. The figure shows a circuit diagram of the preamplifier. The amplifier design provides for a flat frequency response between 10 Hz and 1 kHz with a CMRR of 100 dB at the mains frequency. The two ICs in the input stage act as voltage followers, which present the desired high input impedance to the electrodes. They are coupled via the capacitor C1 and resistance R5 to provide a high differential signal gain. Capacitor C1 determines the low frequency performance of the circuit. It also eliminates the effects of any DC offsets due to IC1 and 2 or any imbalance in electrode potentials at the output. The second stage EC3 provides further differential signal gain while rejecting common mode signals. The overall gain of the amplifier is 1000. Low frequency and high frequency filters in the system are used to select the passband of the incoming signal and to modify the progressive reduction in voltage output which occurs at either end of the frequency spectrum roll-off. Sometimes it is necessary to examine the signals from individual fibers of muscle tissue. For this purpose, special needles are available with a 25 micron diameter electrode surface and up to 14 pickup surfaces down the side of one needle. These 14 points are scanned sequentially to determine which point is acquiring the largest signal. This point is then considered as a reference signal and its signal is used to trigger the sweep. Signals from the remaining 13 points are then scanned sequentially and recorded with respect to the reference signal. To examine the signals, it is necessary to trigger the sweep from the signal and to delay the signal so that the whole of its leading edge is displayed. Integrator is used for quantifying the activity of a muscle. The integrator operates by rectifying an incoming EMG signal, that is by converting all the negative potentials to identical positive deflections so that the EMG pattern consists of positive deflections only. The area under rectified potentials is accumulated using a low-pass filter so that the module output at any time represents the total area summed from a selected starting time. The integrator indicates the EMG activity either as a variable frequency sawtooth waveform or as a steady deflection. The stimulators incorporated in the EMG machines are used for providing a single or double pulse or train of pulses. Stimulus amplitude, duration, repetition and delay are all adjustable and facilities are provided for external triggering also. Nerve conduction velocity. Nerve conduction velocity measures the speed at which an electrical impulse travels along a nerve. Nerve conduction velocity or NCV can identify nerve damage since healthy nerves send electrical signals more quickly and with greater strength than damaged nerves. An NCV test can be used to diagnose a number of muscular and neuromuscular disorders. The figure shows how nerve conduction velocity is measured. Two electrodes are attached to the subject's skin over the nerve being tested. Electrical impulses are sent through one electrode to stimulate the nerve. The second electrode records the impulse sent through the nerve as a result of stimulation. The time difference between stimulation from the first electrode and pickup by the downstream electrode is known as the latency, which will be in the order of milliseconds. The distance between the stimulating and receiving electrodes is divided by the impulse latency, resulting in conduction velocity. Many times, EMG is also performed on subjects at the same time as other NCS procedures because they aid in detecting whether muscles are functioning properly in response to the stimuli sent via their connecting nerves. Thank you.